Hi, I'm Jim Frankenfield, and this is another quick problem solution for a physics problem in the electrical circuits topic. This was posted on my own help group, the Math and Physics group on Facebook, and I'm recording this. I'm going to post a quick raw recording on Facebook, and then I'll be editing this to put it on my YouTube channel. The circuit's pretty straightforward, but it has kind of an interesting twist, and the algebra might throw some people off a little bit. That's why I decided to do this on video. So let's take a look at the problem here. All right, we have what's really a pretty simple circuit. All of these three resistors here are resistance R1, and this one is R0. And we need to remember our equations for resistors. So when they're in series, we add the resistances. When they're in parallel, we have 1 over R1 plus 1 over R2 gives me 1 over my equivalent resistance. And you can simplify that to this form here. So I'm going to use these two basic equations for resistors in series and resistors in parallel and simplify the circuit. The catch in this problem that makes it a little interesting is that you want the equivalent resistance in the end to equal just R0. So in that case, you could basically throw away 3 resistors and just have R0. So let's see if we can do that. Let's start by simplifying this part of the circuit, and that is simply R0 plus R1. Those are in series. Okay. Now those that are in series are in parallel with R1. So I need to take this quantity and put it in parallel with R1. So I'm going to have R1 times this and R1 plus this. So in the top, I'm going to have R1 times this quantity. And now I have a denominator, and I'm going to have R1 plus this quantity. So I'm going to have 2R1 plus R0. So this is the resistance for the part in red. And now I'm going to add R1. And when I'm all done, this needs to equal R0. So this is the basic setup from my physics resistor network series and parallel equations. And this is the physics. Physics is essentially done here. But we have to solve this equation to find out what R1 is in terms of R0. And this, at first glance, does not look very friendly. And this is why I decided to make a video of it. This might just intimidate people or throw them off. But let's start by getting a common denominator. So let's put the R1 over to R1 plus R0. And in the top, multiply this by 2R1 plus R0. And over here, let's just put this over here. I'm going to do the same thing. I need a 2R1 plus R0 in the bottom. And in the top, I'm going to multiply by that. So 2R1 plus R0. So I've basically multiplied R1 by 1, taking this fraction to use the common denominator I want, and I've multiplied R0 by 1 using that same denominator. So now I'm going to have in the top, let's see, I'm going to have R0 plus R0 R1 plus R1 squared. And from here, I'm going to have a 2R1 squared. And here I'm going to have R1 times R0. And then I'm going to subtract what I have on this side. So I'm going to subtract 2R1 R0. And I'm going to subtract an R0 squared. And this has got to equal 0. And this was all over 2R1 plus R0. But I don't care about the denominator anymore, because to be 0, the numerator needs to be 0. And these are all positive quantities. Okay, I'm assuming we don't have any zero resistances, and resistance can't be negative. So we can simplify the top. We need to set this top part equal to 0. And we have an R0, R1, an R0, R1, and two R0, R1 subtracted, so those actually go away. So what I get is R1 squared minus R0. This was an R1 squared and a 2R1 squared. 3R1 squared minus R0 squared equals 0. Which means that R1 squared has to equal 1 over 3 R0 squared. R1 is equal to 1 over the square root of 3 R0, and that'll do it. And I don't like irrational numbers in my denominators, so I'm going to write that as a square root of 3 over 3 times R0. I'm going to rationalize that denominator. You can go back and check this. You can put this expression back into the circuit or back into one of your previous expressions up here, and you'll find that it works. You could also try values. If you try, let's see, if R0 is the square root of 3, R1 will be 1. That's pretty reasonable numbers to work with to check. And this only checks one case. There's always a small chance that your one test case works and it doesn't work in general. But you can check this either in general or just do a quick test case like this. And if you do this, you'll find out that your equivalent resistance is the square root of 3, which is R0. Anyway, you can test that and check that in a number of ways, and that's how you do that problem. The physics is pretty straightforward. Series resistors follow this rule, parallel resistors follow this rule, and you start somewhere inside and you work your way out till you get back to the terminals at the beginning, that where you want the equivalent resistance. So we got an equivalent resistance expression, which was this part. And I set that equal to R0, which is what the problem asked me to do, which was this part. And then I just found a common denominator, and from there the algebra worked out pretty simply. So if you don't take this step here, I think this is where it gets confusing. You look at this and you add R1, and you've got solve for R1s, and you've got them all over the place, including the denominator. And I think some students wouldn't know where to go next with that. But if you find the common denominator and set the numerator equal to 0, then it works out pretty nicely. So that's how you do that resistor problem. I hope that's helpful to the person who asked, and maybe to some other people who find it as well. And I think I'll probably be adding this to the YouTube channel.